All right. Now, so today we are going to look at momentum. Now, momentum, we're going to do it in two stages, 1D and 2D. So the first few days is going to be, the first few sections is going to be in one dimension, and then we will try to put everything in two dimension on the very last portion of this. Now, so when you hear the word momentum, it means, what does that mean for you? Right. So when you hear the sport announcer say, one team has all the momentum, what does that mean? That means they have, it's kind of like when you're running, for example, or when a car is traveling or when you're running, and momentum seems to be related to something moving, right? So when we say a car has momentum, it seems like, that car is moving, and, when something is moving, usually that is depending on, two things, right? So a moving object is something that has momentum. So it has to be a moving object. So an object that's not moving does not have momentum. Okay. So momentum is something that comes from a moving object. Now, so when an object is moving, right? When an object is moving, it has a speed, right? A velocity. Now, and the object itself also has, something on its own, the mass, right? So it turns out momentum is a quantity that depends on mass and velocity. And that's it. It depends on mass and velocity. Okay? So any moving object has momentum depending only on two things, mass and velocity. Now, and the equation, there's only one equation in this entire momentum chapter. There's only one. Well, actually two. One is momentum, the other one is called change in momentum, so they count separately. Momentum, we use P, I know, momentum, right? M. But the equation for momentum has mass in it. So if we use M, it will be very confusing. It will be like M equal to M and then V. So the momentum is defined as the product between an object's mass multiplied by how fast it's going. Now, mass doesn't have a direction. We know that, but speed does, right? So velocity does have a direction. So momentum also have a direction. The direction for momentum is the same direction as the speed or the velocity that you're going at. The unit for momentum is the same as the unit for the two things that it consists of combined, which is kg with a speed meter per second. So kg meter per second. So the unit for momentum is very boring. It's literally kg meter per second. Okay, it's combining the units for kilogram, the unit kilogram for mass, and the unit meter per second for speed. Okay, so in this equation, that's the only equation. And look at how simple that equation is. It's two things multiplied together. That's not even, you don't even have to do adding, subtracting. It's very simple. So momentum. Okay, now, okay, so it should be very simple then, right? So P is momentum, M is the mass, and V is the velocity. Now, make sure that your velocity has direction in it because your momentum also will use the same direction. Mass doesn't have any units, so you can basically ignore that. So you have kilogram for mass, kg meter per second, kg meter per second for momentum, and velocity is meter per second. So all the units should work out. All right. Now, momentum, as I said earlier, involves direction. So momentum is a vector quantity, meaning that it has both magnitude and direction. So the direction will just be the same direction as the velocity. Now, the unit for momentum, we talked about that briefly already, is kg meter per second. But there is another unit for it. We are leaving it blank right now. We will come back to this in about, like, let's say 20, 30 minutes, and then we will fill in this box, okay? We are leaving this blank because I haven't shown you the second equation for momentum yet, and that will carry another unit. So we're leaving this blank. Okay, so these example questions will be extremely, extremely easy because look at that equation. I mean, how hard can I make that question when the equation is mass times velocity? Like, what can I do, right? Okay, so look at what is the momentum of, it's near Halloween. appropriately, pumpkin. What is the momentum of a pumpkin traveling at 5 meters per second? So momentum is mv. The pumpkin is with 6.2 kilogram. So you do mass first, and then velocity, which is 5 meters per second. Now you have to make sure the unit works. So mass has to be in kilogram, speed has to be in meter per second. None of those km per hour nonsense. With car question, you have a lot of km per hour. Convert it back first, right? Multiply together, you get about 31 kg meter per second. But watch out. This will be, so for example, let's say this is your answer, right? At the end, then Mr. Chung gives you 3 or 4, and then you're like, oh, why do I lose 1 mark? Momentum has direction, my friend. Did you give me a direction? No, you did not. So lose 1 mark. West is the direction of the speed. So you have to watch out. It's somehow like a lot of time is hidden somewhere. I mean, if you know which way the object is going, the momentum is in that direction also. Okay, so this object has a momentum of 31 kg meter per second. Now, momentum also sometimes represent like impact, like how much damage something can do. So the higher the momentum value of an object, the more damage it can do when they impact something. So for example, that's the reason why, you know, like elephant running toward you, even though elephant doesn't run really fast, right? We know that. Elephant doesn't run really fast. They basically just walk to you. But when elephant walks to you, you still get like, and they run into you, you still get injured. Because even though the speed is small, right? The mass is enormous. So the momentum is still a very, very big number. Now, why does bullet hurt? Why does bullet hurt? Bullet is really light, right? Bullet is only half a kilogram. Why does bullet hurt? Because even though the velocity is really small, but the mass is really small, isn't the velocity of a bullet very big though, right? So it will still carry a lot of momentum, therefore it can do damage. So in order to increase momentum, which is increasing the damage of something, you can think of it in 2 ways. You either increase the mass of the object that you're using as your projectile, or you increase the speed of the projectile. Either one way, you can increase the damage output, which is kind of like the momentum in this case, right? So that's why, you know, slow moving dinosaurs are still deadly. Fast moving bullets are also very deadly, right? So it depends on the multiplications of the two. Now, baseball. Now, baseball has a mass of a couple 100 grams, 140 grams in this case, traveling at 35 meters per second. Find the momentum of the baseball. Again, one very easy application. These will go through in like seconds. So 0.14 is the mass. And then we have my kilogram has just collapsed into just an L. There you go. And 35 meters per second. And momentum is 40-ish. 4.9 kg meter per second. Now, I look at this question, right? I don't see any direction. If the question did not give you a direction, it's okay to not give a direction at the end, because I don't even know what that speed is going at, maybe north or east, I don't know. The question didn't say. Then it's okay to have one, to not have any. Now, but instead of throwing a baseball at you, what if I throw a bowling ball at you? That sounds bad, right? So how fast would a bowling ball need to travel to have the same momentum as the baseball? Now, so the baseball has a momentum. This is the baseball, right? So I want the bowling ball to have the same momentum as the baseball. So I want the momentum of my bowling ball to be the same as the baseball, which is 4.9. Okay, now, but the mass of the bowling ball is different. So the mass of the bowling ball is different. So the speed will also be different. The mass of the bowling ball, let's say, is 7.6 kilogram. So how do you find the speed? Divide both sides by that, right? So algebra, approximately 0.64 meter per second. Now, what you want to notice in here is, look at how fast the baseball have to go, 35 meters per second, and look at how fast the bowling ball had to go, only 0.6 meters per second. And they will have the same amount of momentum, right? Because the bowling ball is just so much bigger, right? Okay. All right, so that equation is easy, all the examples that we have done. Now, let's do some change. So one of the things that you need to calculate a lot is change in momentum. Not just momentum, but the change in momentum. Because the concept of momentum, right? You look at the equation, very easy. Why do I say we have to spend, let's say, 2 or 3 classes on this still? Well, it's because momentum is specifically good at one type of situation, and that is collisions. It's figuring out collisions between objects, like objects that are colliding head-on, objects that are colliding rear-ended, any objects that are colliding with other objects and bouncing back. That is when momentum is the best for. So we have a theory that will come in a little bit that will just called conservation momentum that will help us do all type of accidents, like head-on collision, rear-ended collision, bouncing back collision, sticking together after collision. Any type of collisions can be dealt with as long as we have the concepts of conservation momentum. So we're just doing the basic stuff right now first. Now, but before we do conservation of momentum, we have to know how to do change in momentum. That means, for example, if you're running really fast, you have momentum. But what if you hit the wall? You don't have momentum after, right? So because your momentum based on your speed, if you hit the wall, you stop. So how do you calculate change in momentum is the next thing. In science, again, one reminder, change is usually met with this triangular, it's delta, right? Delta. So change is delta. So change in momentum is delta P. Okay, change in momentum. As with anything in science, change in any quantity is final minus initial, always. Not the other way around. Okay, it's always final minus initial. All right. Now, so if you know the final momentum, subtract by the initial momentum, then you will get the change in momentum. So that means you have to draw a picture because you need to find out what is final, what is initial. So let's say there is a water balloon. Now, so here's my attempt to draw a water balloon and with water inside, and it's moving at a speed of 32 meters per second. And then come to a stop because you hit the wall. Okay, so a wall. The water balloon hits the wall, and then it stops. Okay, so we have a initial and final picture. Initially, you have a speed VI, and at the end, you have a speed V final. And I argue that your V final is 0 because you hit the wall. All right, so your box is going like, the ball is going this way. Okay, so we're going to figure out your initial momentum and your final momentum. So if you want to find out the change in momentum, we will subtract them. So change in momentum is final momentum minus initial momentum. However, which is basically this equation if everything is in 1D, mv final minus mv initial. Yep. Okay. Yep. So, but V final is 0 because you hit the wall. So therefore, the first part of this equation is already gone. And you just have the mv initial. That's the change in momentum. Oh, that's easy. So it's going to be negative 0.5 kilogram multiplied by the speed, which is 32. Now, that is very easy to figure out. So that's negative, for example, 16 kg meter per second. So that's your change in momentum when you hit the wall. Okay, so change in momentum. So that's how much impact you're doing to the wall. Now, but what if you have exactly the same scenario? However, this time, instead of a water balloon, this thing is now a bouncy ball. You know, one of these bouncy ball. So when it hits the wall, it's not going to stop there. It's actually going to bounce back. Okay. So the situation is going to be you have a wall and the object goes forward, same speed. Let's pick the same speed. So we initial 32 meter per second, same speed. Okay, but it's a bouncy ball. So instead of actually sticking onto the wall, it's going to bounce off from the wall. Okay, so the ball will hit the wall, like momentarily it's going to be like deforming, and then it will go back to its original size and shape, and then it's going to travel backward like this. Okay, so now in this question, they say, assuming that the bouncing back is the same speed. Okay, same speed it is. But that is not okay. Okay, so you have to be careful about directions. So remember, momentum has direction. So your speed has to have direction, your velocity. If one object is going to the right and later on is going to the left, that means you have to either say the right is negative or the left is negative. You cannot say both of these two speeds is 32. One of them has to be negative 32 because it points in the opposite direction. Now, in our everyday life, we kind of make it a habit to put the right-hand side object as positive and the left-hand side object as negative. So we are going to do that, but it's up to you. One of them has to be negative, whichever one. Okay, so that's bouncing back. Now, you're changing momentum. This time, it's going to be ME final minus ME initial again, right? Because it's momentum final minus momentum initial. But your V final is no longer 0. So change in momentum is equal to mass times V final, which is no longer 0, is negative 32, minus 0.5 again, and 32. 32. Okay. So these two numbers are both negative. When you subtract them, they're actually just adding to each other, but become even more negative. So if you get the final result, this is negative 32. kg meter per second is the unit. Now, I want you to compare these two answers. Stopping something versus bouncing it back. So this is for stopping it. This is for bouncing it back. Okay. Now, remember, momentum is kind of like impact, right? So impact on what? Impact on the wall. But imagine, I mean, in PE class, have you ever been selected as the goalie of like a football game, right? So when the attacker from the opposing team try to shoot the ball and you try to stop it, you have two options: catch the ball or bounce it back, right? Okay, you either catch the ball or you bounce it back. This is exactly that situation if you replace the wall with yourself. Now, but look at that. Stopping the ball only requires a change in momentum of negative 16. Bouncing it back requires a change in momentum that is negative 32. That means which way is going to be more damaging to you? Bouncing it back. So it's always easier to just catch the object and make it stop than to go like punch the ball back. That will cause more stress on, you know, your fist, for example, if you are the goalie. Or when someone throws you something, it's always better to just stop it versus punching it back. It doesn't matter what it is, a ball, a basketball, or someone throw you an apple. So instead of catching it, you decide to for some reason, just like punch it back, that hurts more than catching it. Okay, so the change in momentum is going to be some kind of an impact on you. So for example, the water balloon will do less damage on the wall compared to the bouncy ball. So if you keep doing that, for example, the water balloon will not do too much damage to the wall, but the bouncy ball, every time it bounces back, do more damage that way. Okay, so now let's that in here.